My name is MIKIO KUBO from Tokyo University of Marine Science of Technology. The title of this talk is Supply Chain Optimization. This is the agenda of this lecture. I will start with the definition of the supply chain and logistics, and introduce 3 decision levels of the SC, and then show you the classification of inventory. Next I'm going to talk about several models in the SC. They are logistics network design, inventory, production planning, and vehicle routing. There are many definitions of the supply chain. But my definition is simple. IT, that means the information technology, plus logistics equals supply chain. To complete the definition, we need the definition of logistics. As shown in this figure, logistics optimizes the flow of products between the point of origin, here supply point, and the point of consumption, here demand point, in order to meet customers' requirements. In general, the supply chain is composed of 3 systems. One is the real system that includes real logistics objects such as trucks, ships, plants, products, machines, etc. Using the metaphor of human beings, the real system is compared to muscle of the body. In the past, many companies have real systems only, that means no IT. But recently all advanced companies own some IT, so-called transactional IT, for example, POS, that means point of sales. You can see such a system in convenience stores or supermarkets. ERP, that means enterprise resource planning, that is an extension of legacy MRP, that means material requirement planning, etc. The transactional IT is compared to a nerve net of human beings that just flows the pulse and executes some automatic actions. More modern IT system is called the analytic IT, that is composed of some models and algorithms to solve them. The objective of the analytic IT is to help the decision maker. It is compared to the brain of human beings. That's the main theme of this talk. The decision support systems or analytic IT models can be categorized into 3 levels. The top level is the strategic level that deals with decisions that have a long-time effect that spans from a few years to 10 or more years. Typical decisions in this level are the number, location, and capacity of warehouses and manufacturing plants, and the flow of material through the logistics network. The tactical level includes decisions which are typically updated between once every month or quarter, or once every year. These include purchasing and production decisions, inventory policies, and transportation strategies. Finally, the operational level refers to day-to-day or real-time decisions such as scheduling, dispatching, vehicle routing, and truck loading. Using some metaphors, the strategic level is compared to seeing the forest, while the operational level is compared to seeing the tree. Such a change of the point of view is quite important for the decision-making using analytic IT models. This figure represents an entire supply chain. Procurement of parts or raw materials from suppliers, production at plants, stocking in DCs or warehouses, and distribution to retailers. These are the decision levels: strategic, tactical, and operational, that means long-term, middle-term, and short-term, respectively. In the strategic level, we have an analytic IT model named the logistics network design that encompasses the whole logistics network and determines new suppliers, a new flow pattern of products through the network, a selection of warehouse locations and capacities, the production levels at each plant or the production line in order to minimize total production, inventory, and transportation costs, that means whole supply chain costs. In the tactical and operational levels, we have 3 types of models. They are inventory, production planning, and transportation delivery optimization models. The safety stock allocation model, that is used in the tactical level, determines the positions of safety stocks in the supply chain, and simultaneously determines the pull-push boundary of each product. The inventory policy optimization model, that is in the operational or tactical level, decides at what point to reorder and how much to order so as to minimize inventory ordering and holding costs. Production planning optimizes the acquisition of resources such as machines or workers, the size of the production lots to be manufactured or processed in a batch, these are in the tactical level, and the sequencing of the production lots, it's usually in the operational level. Finally, transportation delivery optimization involves the routes and frequencies of vehicles such as ships or trucks. The most important transportation delivery model is the vehicle routing problem that occurs at the final part of the supply chain, that means the final distribution of products to the retailers or customers. It is in both tactical and operational levels. Inventory plays an important role in the supply chain. Using the metaphor of human body, inventory is compared to blood and it acts as glue connecting several processes in the SC. Inventory is spread throughout the SC from raw materials, work in process, WIP, inventory, to finished products in warehouses and retailers. And such inventory varies day by day or period to period due to many reasons. To understand the role of inventory in the SC, we need to classify it into 5 categories by their motivations. They are in-transit inventory, seasonal inventory, cycle inventory, lot size inventory, and safety inventory. We have to ask why we have such inventory every time we encounter inventory in the SC. In other words, we must optimize the trade-offs between inventory and some other factors. In-transit inventory is inventory moving through the arc or link in the SC. It can be seen as a flow through a pipeline, so it's sometimes called pipeline inventory. Such inventory exists because transportation time is positive. In-transit inventory is proportional to the flow volume and transportation time. That means if the speed of the flow is faster, in-transit inventory becomes smaller. This inventory will be treated and be optimized in the logistics network design model. The main role of inventory in the SC is to fill the gap between supply and demand. Seasonal inventory is inventory to counter predictable seasonal demand under the restriction of the limited production resources. For example, a can maker supplies tons of cans to beverage makers such as beer companies. For a high demand during the summer season, the can maker builds up inventory during low demand periods and store it. This is seasonal inventory. Assume that demand is constant and supply arrives cyclically. In this case, inventory changes like saw teeth. Here, saw is a tool for cutting woods whose teeth is like this figure. That's cycle inventory. Many activities in the SC have economy of scale, that means large lots decrease the cost. This is the motivation of cycle inventory. If transportation activity has a non-negative fixed cost, we have to have cyclic inventory, which is optimized in the LND model. If ordering activity has a non-negative fixed cost, we have to have cyclic inventory, which is optimized in the EQO model. Lot sizing inventory is a generalization of cycle inventory when the speed of the demand is not constant. That means the demand changes over time, period by period. As in cycle inventory, lot sizing inventory has the trade-off for fixed costs, especially production setup costs, and is optimized in lot sizing and multi-period logistics network design models. Safety inventory or safety stock is inventory to protect against uncertainties of future events such as customer demands. So it has the trade-off for the customer service level. If customers request 100% of service level, that means no stock out, retailers need a huge amount of safety inventory. Service level is determined by backorder or stockout penalty costs. So there's a trade-off between safety inventory costs and backorder costs. Many analytic IT models include safety inventory. They are safety stock allocation, logistics network design, and inventory policy optimization models. Inventory can be classified into these 5 types of inventory: in transit, seasonal, cycle or lot size, and safety inventory. It's not so easy to treat them separately in practice. But we should optimize them separately using some analytic IT models. I'll talk about such models until my lecture time is up. The first model is the logistics network design, which involves issues relating to plant, warehouse, and retailer locations. These are strategic decisions because they have a long-term effect on the company. The objective is to design or reconfigure the logistics network so as to minimize annual system-wide costs, including production and purchasing costs, inventory holding costs, facility costs that include storage, handling, and fixed costs, and transportation costs. There are many decisions optimized in this model. For example, where should we replenish parts? In which plant or on which production line should we produce products? Where and by which transportation mode should we transport products? Where should we construct or close plants or new distribution centers? There are many trade-offs in the model. For example, increasing the number of warehouses typically yields an improvement in service level due to the reduction in average travel time to the customers. An increase in inventory costs due to increased safety stocks required to protect each warehouse against uncertainties in customer demands. An increase in overhead and setup costs. A reduction in outbound transportation costs from the warehouses to the customers. An increase in inbound transportation costs from the suppliers and/or manufacturers to the warehouses. Another trade-off in the LND model is between the in-transit inventory cost and the transportation cost. In-transit inventory is proportional to the flow volume and transportation time. So if we use a fast transportation mode such as a plane that is expensive, in-transit inventory becomes smaller and decrease the inventory cost. Meanwhile, if we use a slow transportation mode such as a ship, in-transit inventory becomes larger. That's the trade-off and should be optimized in the LND model that selects the appropriate transportation mode for each link by minimizing the sum of the transportation and in-transit inventory costs. We can extend the basic LND model to the multi-period LND model. Let us consider situations where demand changes over time because of seasonal factors, or growing or shrinking markers. It also allows for time-varying purchase, production, transportation, and inventory costs. The problem is to find the right balance between the cost of holding seasonal inventory and the other costs. This model is in the tactical decision level and can be seen as an extension of the Master Production System, MPS, usually used in a plant for determining the production level. The multi-period LND model optimizes the trade-off between seasonal inventory cost and overtime penalty cost. Assume that demand has a seasonal peak, say in summer, and our plant has a limited resource. So we cannot supply the peak demand by the production during the peak periods. One strategy to cope with the peak demand is the so-called constant production strategy using seasonal inventory. That means the company builds up inventory during low demand periods, say in spring, and stores it for the summer, the peak season. Another strategy is to vary the production level by hiring new workers or by doing overwork. Both require additional costs. The multi-period LND model finds the best balance of these strategies. The LND model can be formulated as a multi-commodity network flow problem. Supply chain or logistics network is modeled as a network composed of nodes and arcs. The raw materials, parts, intermediates, final products or items are modeled as commodities or flow through the network. We have to model the bill of material, BOM, or recipe structure that represents the relationship between the items. That means which product is composed of which parts or raw materials. We also incorporate the safety inventory cost into the model that is a concave function of the flow volume through the arc due to statistical economy of scale that we'll discuss later. Usually, the concave cost minimization problem is difficult. It is called NP-hard. That means it's probably impossible to find an efficient algorithm to solve it in general. But by using approximation of concave functions, the LND problem can be formulated as a mixed integer programming problem and can be solved by standard MIP solvers. Here MIP means mixed integer programming, such as CPlex, ExpressMP, they are commercial solvers, or GLPK, SCIP, they are free solvers. The LND problem can be formulated in mixed integer programming, or MIP in short. But it is too complicated to discuss with here. So I'll show you a simpler model named the Simple Facility Location Problem that is a submodel of the LND problem. We are given two sets I and J where I represents the set of customers and J represents the set of plants. Each customer demand is scaled to 1 and must be satisfied. Each plant has a fixed cost F_J that is incurred when it is open. We also need a transportation cost C_ij from plant J to customer I. We use two variables, x and y. X represents the flow volume from plant to customer, while y is a binary variable that represents the open or closed decision of the plant. The objective function to be minimized is the sum of the fixed and transportation costs. The first constraint means that every customer demand must be satisfied. The second constraint forces the plant to be open if some products are shipped from the plant. By using a MIP solver, we can solve this problem easily if the problem size is not so large. If the problem is too large to be solved by MIP solvers, you can use specialized algorithms such as Lagrangian relaxation or Bender's decomposition. But both are beyond the scope of this lecture. The second model is the safety stock allocation model in the tactical level that optimizes the trade-off between the safety inventory and the customer service level. This model is based on a basic principle of inventory called the statistical economy of scale. That means gathering inventory together reduces the total inventory volume and cost. This principle is used in many modern supply chain strategies such as risk pooling, delayed differentiation, and design for logistics. The safety stock allocation model answers how to use these strategies and also answers the following questions: where to keep safety stock? Which facility should produce to stock? And which facility should produce to order? The safety stock allocation model is based on the classical formula to compute the safety inventory volume. Assume that the demand follows the normal distribution with average demand U and the standard deviation sigma. Service level is the probability of no stocking out and is determined by a decision maker. Lead time is the amount of time that elapses from the instant that an order is placed until it arrives. So the maximum inventory volume is computed by the formula mu times L plus safety stock ratio sigma times square root of L. Here, safety stock ratio can be computed from service level. If the service level is 95%, then the safety stock ratio becomes 1.65. Actually, this formula is a special case of the classical newsboy problem that I will talk later. This figure represents the relationship between the lead time and the average, safety, and maximum inventory. Horizontal axis is the lead time and the vertical axis is the inventory volume. Average inventory, drawn in black line, is a linear function, while maximum inventory, drawn in pink, and safety inventory, drawn in yellow, are both concave. That represents the statistical economy of scale. One characteristic of the safety stock allocation model is to treat lead time as a variable instead of a given constant. First, we introduce the guaranteed lead time, that is a committed time that the facility guarantees to deliver to its customers. In this example, this facility I guarantees to deliver to its customers within 2 days, represented by a yellow arrow in the upper right corner. So the guaranteed lead time denoted by Li is 2. This facility has another lead time called the entering LT, that is the GLT of his predecessor or upstream supply facility. In this example, the entering LT of facility I represented by a yellow arrow in the lower left corner is 1 because its predecessor has GLT 1 day. The facility has a given constant production time, that is the amount of time that elapses from the instant that the item or product arrives until it is ready to ship. In this example, it is represented by a green rectangle in the lower right corner and it is 3 day. The net replenishment time is defined by entering LT plus production time, guaranteed LT. In this example, the net replenishment time represented by the red arrow in the upper left corner is 1 plus 3 minus 2 is equal to 2. The inventory of the facility is set to the maximum demand volume during the net replenishment time to satisfy the service level. I will show you a small example to clarify the model. The SC consists of 4 facilities in serial. The first facility is the supplier of parts, the second one is the plant, the third one is the wholesaler, and the final one is the retailer. The retailer has a random demand. We assume that the demand follows a truncated normal distribution whose average is 100 and standard deviation is 100. Each facility has a service level whose safety stock ratio is 1. The production time of the facilities is 3, 2, 1, 1, in order, and inventory cost per unit volume per day is 10, 20, 30, 40, in order. Notice that the inventory costs are increasing because the supply chain adds some values to the item, and the inventory holding cost increases as the value of the item increases. If the guaranteed lead times of all facilities are 0, the total safety stock cost, represented by red arrows, becomes $11,560. By using some optimization algorithms that we discuss later, we get an optimal solution of this problem easily. If we fix the guaranteed LT to the customer to 0 and also fix the guaranteed LT from the supplier of the parts maker to 0, the optimal safety inventory cost becomes $9,732. We could save about 16% from the base model. At the wholesaler, the guaranteed LT is 3 and the entering LT is 2. So the net replenishment time becomes 2 plus 1 minus 3 is equal to 0. That means no safety inventory at the wholesaler. In this case, the pull-push boundary is on the retailer. All other facilities produce to fill the stocks of the retailer, that is, push system. If we relax the guaranteed LT to the customer from 0 to 1, we can save more money. The optimal inventory cost becomes $6,928. We could save about 40% from the base model. The pull-push boundary moves to the upstream point, from the retailer to the wholesaler. The wholesaler and the retailer produce to order, while the parts maker and the plant produce to stock. Next, I'll show you several algorithms for solving the safety stock allocation problem. First, we consider dynamic programming algorithm for a special case, called serial multi-stage model, because the general case is too complicated to discuss here. Our serial SC system is composed of n facilities. Facility 1 is the demand point, Facility 2 supplies 1, 3 supplies 2, and finally Facility n supplies Facility n1. We assume the supplier of Facility n, denoted by n plus 1, has enough inventory, i.e., no stockout. This is a recursive equation of dynamic programming. Here f_i is the minimum cost from facility n to facility i when the guaranteed LT of facility i is L_i. Function f_i, L_i, can be computed from f_i plus 1, that is the minimum value of f_i plus 1, plus safety inventory cost at facility I when the guaranteed lead time of facility I plus 1, that is the entering LT of facility I, is L_i plus 1. In this case, the net replenishment time at facility I becomes L_i plus 1, plus T_i, production time, L_i and D denotes the maximum demand function. We can compute all the functions f starting from the initial or boundary condition f_n plus 1 outside suppler, is all 0 for all guaranteed lead time L. By calculating f_n, f_n1, in order, we can compute f_1, that is the minimum cost from facility n to facility 1, that is, by definition, the value of an optimal solution. Next, I'll show you a mathematical programming approach for solving the safety stock allocation problem in general network. The main variable is x that represents the net replenishment time. The objective function is nonlinear. Here d is the maximum demand function. It is a general nonlinear function. D minus ux gives us the safety inventory volume, and by multiplying it by holding cost h_i, we get the safety inventory cost. The objective function is the sum of these nonlinear functions over all facilities. The first constraint defines the net replenishment time is equal to entering LT_i, it is a variable. Plus processing time T_i, it is a constant. Guaranteed lead timely, it is also a variable. The second constraint means that the entering lead time of facility J is greater than or equal to the guaranteed lead time of facility I if there exits an arc between I and J, i.e., facility I is a supplier of facility J. The third constraint restricts the lower and upper bounds of the guaranteed LT, and finally, the fourth constraint defines the non-negativity of the net replenishment time. This is a nonlinear programming problem. Generally it's quite hard to solve it, theoretically, it's NP-hard problem, but by using some piecewise linear approximations of nonlinear functions, we can solve the problem by standard MIP solvers. In summary, the safety stock allocation problem can be solved by several types of algorithms. The first one is based on dynamic programming. We can extend the DP algorithm we discussed to a more general tree network case. But, unfortunately, we cannot extend the DP approach to general networks. The second one is the mathematical programming approach that relies on MIP solvers. It can handle middle-size instances with general networks. Other approaches are metaheuristics such as local search, iterated LS, or taboo search, etc. They give approximate solutions instead of the exact solutions, but it's usually faster and more robust. Here is a real example reported in the book written by David Simchi-Levi of MIT. Final demand, part 1 in this figure, is sold in Dallas that has a normal distribution with average 100 and standard deviation 10 and customers guaranteed LT is 30 days. Many parts are required to produce the final product and they are produced in many facilities. By optimizing the allocation of safety inventory, they could save more than $43,000. It's about 40% cost down from the baseline model. The safety stock allocation model can be used in so-called what-if analysis, too. For example, what if we change the guaranteed lead time to the customer from 30 days to 15 days? That means an improved customer service. The model answers the question. The cost increases to $51,000. Next we will turn our attention to another inventory model called inventory policy optimization. Inventory policy optimization is in the operational or tactical decision level. We first introduced two classical models, Newsboy model and economic ordering quantity model. The Newsboy model introduced by Scarf in 1960 is a framework where we optimize the trade-off between lost sales and safety inventory costs. The EOQ model introduced by Harris in 1915, not 50, it's a very old model, is a framework where we optimize the trade-off between fixed ordering and cycle inventory costs. First we consider the economic ordering quantity model, EOQ model in short, that determines the optimal order quantity and simultaneously finds the optimal cycle time. These are the notations of the model. Here D is a constant demand rate, Q represents the order quantity that's a variable. K denotes the fixed setup cost of an order, and H is the inventory holding cost per unit item per unit time. The objective of the model is to find the optimal ordering policy that minimizes the sum of fixed ordering and cycle inventory costs over infinite planning horizon. To find the optimal policy, we consider the inventory level as a function of time as shown in this figure. Without loss of generality, we can assume that initial inventory is 0 and the lead time is also 0. Inventory level becomes the so-called sawtooth pattern. The time between two successive orders is called cycle time, denoted by T. It's a variable. The total cost in a cycle of length T is K plus HTQ/2 where K is the fixed ordering cost and Q/2 is the average inventory level. So HTQ/2 is the inventory holding cost during the cycle. Since D equals Q/T, the average cost per unit time becomes K/T plus HDT/2. Since we'd like to minimize F, T, we compute the derivative of F and also the second-order derivative. This is the first-order derivative. This is the second-order derivative. The second-order derivative of f is always positive cause both k and t are positive. This indicates the function f is convex. By solving the equation that the first-order derivative is equal to 0, we get the optimal cycle time t asterisk equals square root of 2k/hd and the optimal objective function value is square root of 2k/hd. By substitution, we get the optimal ordering quantity q asterisk that is square root of 2kd/h. This is called the EOQ or Harris's formula. Next we consider another classical inventory model, namely the newsboy problem in which a single product is to be ordered at the beginning of a period and can be used only to satisfy demand during that period. Here, H denotes the inventory cost per unit of positive inventory remaining at the end of the period, and B is the lost sales cost per unit unsatisfied demand that is incurred when the ending inventory is negative. The demand D is a non-native random variable with distribution function capital F and density function F. The decision variable S is the number of units to be ordered at the beginning of the period. Our goal is to find the optimum ordering quantity S that minimizes the expected costs incurred at the end of the period. The expected cost CS is computed as the expectation of the sum of the inventory cost and the lost sales cost. Using the rules for taking the expected value of a function with random variables, we obtain this formula. By taking the derivative and the second-order derivative of CS, we get the optimality condition. Because the second-order derivative is always positive, we get the minimum by setting the first-order derivative equals 0. So the optimal ordering quantity S asterisk should satisfy F, S asterisk, equals B plus H. This ratio B plus H, is called the critical ratio. This formula indicates that it is optimal to set the service level to the critical ratio. Newsboy model can be extended to multi-period model in which the ending inventory at a period becomes the starting inventory of the next period. In this case we have to monitor the inventory position that is defined as the sum of in-hand or local inventory plus inventory on order, that means the amount of orders that has not been arrived yet, backorder, that means demand not satisfied now but carried over to future. We determine the ordering quantity so that the inventory position becomes a predetermined value called the base stock level, that is the base stock policy. This figure shows the change of inventory levels of the base stock policy. This blue line represents the change of in-hand inventory. The inventory position is always constant and equals to the base stock level. If a demand occurs, the in-hand inventory drops but the inventory position is constant, cause the system immediately orders the same amount, then the order arrives after the lead time. If the fixed ordering cost is positive, the base stock policy is no more optimal. In such cases, we need modified base stock policies, namely, Q, R, policy and S, S, policy. In Q, R, policy, we monitor the inventory position and if it reaches a reorder point R, we order a fixed quantity Q. Here R and Q are system parameters. We may use EOQ model to compute the ordering quantity Q. In S, S, policy, we again monitor the inventory position and if it is below a reordering point small s, we order the amount so that the inventory position becomes an order up to level capital S. This figure shows the change of inventory levels of Q, R, and S, S policies. Here is a reorder point R, or small s, and here is the order up to level Q plus R or capital S. When the inventory position becomes R, both policies order the amount Q and the inventory position becomes R plus Q or S. After the lead time, the order arrives and the in-hand inventory increases and coincides with the inventory position. If the bulk demand occurs and the system orders below the reorder point, the Q, R, policy orders Q while the S, S, policy orders more so that the inventory position becomes capital S. Under some reasonable assumptions, S, S, policy is proved to be optimal. But I believe, Q, R, policy is more practical in Japan cause the ordering lot size is fixed in many companies. Next we consider a model in production planning. The first model is the lot size optimization model. This model supports the decision maker in the tactical level and optimizes the trade-off between the setup cost and lot size inventory. This model can be seen as an extension of the EOQ model in which the customer demand is not necessarily constant. First I'll talk about the basic single-item model. Here are the notations. Capital T is the number of periods. We will use small t as an index for the periods. D_T is the demand during period T, F_T is the fixed production setup cost. C_T is the production variable cost. H_T is the holding cost in period T, M_T is the capacity of production in period T, notice that these parameters may be time-dependent. Next we define the variables. It is the amount of inventory at the end of the period. X_t is the production amount in period t, Y_t is a binary variable that is equal to 1 if the production amount X_t is positive, and is equal to 0 otherwise. This variable is sometimes called the setup variable. Using the notations introduced now, I can show you a mathematical programming, more precisely a mixed integer programming, formulation of the lot sizing model. The objective function to be minimized is the sum of fixed setup cost f_t y_t, variable production cost c_t x_t, and inventory holding cost h_t i_t. The first constraint is the flow conservation equation of the inventory. The second constraint connects the production variable, x, and the setup variable, y, and simultaneously specifies that the production upper bound or capacity of the production is M_t. The third constraint defines that the initial inventory is equal to 0. This figure represents the flow model of the basic formulation. The incoming flow to the node representing period t is the inventory from the previous period, I_t1, and the production amount in period t, X_t. The outgoing flow from the node t is the demand D_t and the inventory carried to the next period, I_t. Here X_t is restricted by m times Y_t. When m is a large number, i.e., the uncapacitated case, this constraint gives a weak lower bound, so this formulation is called a weak formulation. To tighten the weak formulation, we can add some additional inequalities called the valid inequalities. Define D_TL as the sum of demands from period t to period L. Let L be the index set 1, small l, and S be a subset of L. Then this inequality called the S-L inequality becomes a valid inequality. Here I'll show you some basic terminologies of mathematical programming, especially polyhedral theory for the guys who are not so familiar in this field. These small circles are the solutions, more precisely the feasible integer solutions. The inequality that includes all the solutions in the half space defined by the inequality is called a valid inequality. The formulation consists of the valid inequalities. These green lines define a formulation but it's weak. The intersection of this formulation and the integer lattice is the set of solutions. The formulation gives us a relaxed solution that is an optimal solution x* of the linear programming relaxation. This blue large circle is the relaxed solution of the weak formulation. The valid inequality that does not include x*, in other words, that cuts off x*, is called a cut or a cutting plane. This blue line is an example of a cut. The tightest or strongest cut is called a facet or a facet defining inequality. This red line is an example of the facet. The ideal formulation is the one consists of facets only. That is called the integer polyhedron or integer hull, cause it is a convex hull of integer solutions. Next we consider an extended formulation that uses an additional set of variables. I'll show you this extended formulation gives the integer polyhedron for the uncapacitated lot sizing model, i.e., the capacity m is a large number. A new variable, X_, denotes the ratio of the amount produced in period S to satisfy the demand in period T. Also define a parameter ch_, that is the cost incurred when we produce in period S to satisfy the demand in period T, that includes the variable production and inventory holding costs from S to T. This figure shows the flow model of this new extended formulation. The flow variable is the ratio of the demand in period T produced in period S. Since X_t is less than or equal to 1, the connection constraint of X and Y becomes simpler X_st equals Y_t. The formulation using the extended variable is called the facility local formulation, cause this structure of the constraints resembles to the simple uncapacitated facility location problem. This is a mixed integer programming formulation of the facility location formulation. This formulation can be shown to be tight, i.e., the linear programming relaxation of this formulation gives an integer feasible solution. We analyze the relationship between the extended formulation and the original formulation. Let X be the set of integer solutions in the n-dimensional space. Q is a formulation in an extended space expanded by a new variable z that is in R to the power of Q-dimensional space. P tilde is the projection of Q onto the original space that is defined as the set of all vectors x in R to the power of n which satisfies the condition that there exists a z such that xz, in capital Q P tilde is a formulation of x if and only if the intersection of P tilde and integer lattice is the set of integer solutions x. In this case, Q is called an extended formulation of x. This figure shows the concept of the projection of the facility location formulation. The original space is here, on the floor. Then we extend the space into three-dimensional space and derive an extended formulation. The above polyhedron or polytope is an extended formulation. If we project this polyhedron on the original space, we get an integer polyhedra. I have talked about two types of formulations of the lot sizing model. The standard formulation requires 0, t, constraints and 0, t, variables where t denotes the number of periods. It's a compact formulation but unfortunately weak. By adding S, L inequalities to cut off the LP optimal solutions, we get a stronger formulation. Actually, if we add all the S, L inequalities whose number is an exponential order of the input size, we get the integer polyhedron. In practice we can add just a fraction of S, L inequalities as a cutting plane. The facility location formulation requires O, t squared, constraints and 0, t squared, variables and it gives the integer polyhedron. In practice the facility location reformulation is much easier to implement. So I recommend this reformulation approach as a first cut. It's not surprising that we could get the integer polyhedron using polynomial numbers of variables and constraints because we can get an optimal solution of the uncapacitated lot sizing problem in polynomial time. Here is an algorithm that is based on dynamic programming. Let capital F, J, denotes the minimum cost over the first j periods. Starting with the initial condition f, 0, equals 0, i.e., the minimum cost to 0 period is 0. We can derive the following recursive equation, that says, the minimum cost to period j is the sum of the minimum cost to period I, that is before j, plus the cost to produce at period I plus 1 and to satisfy all the demand from I plus 1 to j. Based on this dynamic programming recursion, we can derive an O, t squared, or much faster O, t log t, algorithm. We have shown exact formulations and an exact algorithm for the uncapacitated lot sizing problem. For general and large lot sizing problems, it's not so easy to find an exact solution. Here we give some heuristic algorithms for such cases. Notice that the noun heuristics came from Latin language, so heuristics is a singular, not plural. The first one is silver meal heuristics. We introduce a new parameter c, I, j, that is the total cost to produce in period I and to satisfy all the demands from period I to period j. Here f underscore I is the fixed cost, c underscore I times summation of d underscore t means the variable production cost in period I. The third term represents all the holding costs between period I to j. Silver meal heuristics works as follows, starting with period t equals 1, determine the first period j that satisfies this inequality. That means the cost c, I, j, divided by the number of periods attains the minimum value. Then determine the production amount in period t so that it is equal to the total demand from t to j. Then proceed to the next period j plus 1 by setting t equals j plus 1. And repeat the process until we reach the final period t. Next one is a variant of silver meal heuristics called the least unit cost heuristics. As in silver meal heuristics, we first start with t equals 1, the first period, then determine the period j that satisfies this inequality, which implies the cost c, j, divided by the total demand during period I and j attains the minimum value. This criteria means the cost per unit demand. That's the origin of the name of this heuristics, the least unit cost heuristics. The remaining part is the same as silver meal heuristics. I'll show a small example to clarify the lot sizing model and algorithms. Consider a 5-period problem. Here we assume the period unit is a day. These 5 rectangles represent the 5 days, say Monday, Tuesday, Wednesday, Thursday, and Friday. The setup fixed cost is $3. We cannot produce without a setup. The setup is represented by a green circle. The demand is 5, 7, 3, 6, 4 tons for each day. The inventory cost is $1 for 1 ton per day. The production variable cost is time varying, they are 1, 1, 3, 3, 3 for 1 ton of production. The production is represented by a yellow rectangle. One trivial solution approach is to produce at once, that means to produce all the demands on Monday. In this case, the setup occurs on Monday only and the production cost is minimum, cause unit production cost is 1 on Monday. But we have to pay a lot of inventory holding cost, then the total cost becomes $75. Another trivial solution approach is the so-called just-in-time production, that means to produce every day. In this case, the setup cost is large cause we have to set up every day. The total production cost is larger than before, it's $51 cause we have to produce on the days with the higher production cost, Wednesday through Friday. And the total cost becomes $66. Cheaper than the previous approach in this problem. But we can improve the total cost more by using an optimization algorithm. Here is the optimal solution. That is, produce on Monday for Monday's demand, on Tuesday for the demand for these 3 days. And on Friday for Friday's demand. This is the minimum cost $57. You can see all the costs, setup, production, and inventory costs, are balanced. The silver meal heuristics gives this solution, setup on Monday, Tuesday, and Thursday. The total cost is $61, not so bad, but it's not optimal. The least unit cost heuristics gives this solution, setup on Monday, Tuesday, these seems to be a good decision, same as optimal solution. And then on Wednesday. It's not a good decision, cause the unit production cost on Wednesday is increased to $3 from $1. The total cost of this heuristics is $74, worse than silver meal heuristics. The weak point of these heuristics is that they are too myopic. My recommendation for the real lot sizing problems is to use the MIP solver, i.e., the exact solution approach as a subroutine for constructing heuristics or much higher level meta-heuristics. The example of such approaches are the relax and fix, capacity scaling, and MIP-based neighborhood search. The description of these meta-heuristics is beyond the scope of this lecture. Next we consider the second model in production planning. That is the scheduling optimization model. This model supports the decision maker in the operational level and optimizes the allocation of activities over time under the constraints of finite resources. Here activities mean jobs or tasks or operations to be executed, represented by rectangles in this figure. In this example, we have 3 machines as finite resources. The history of the scheduling theory is long, so many researchers have been proposed a number of algorithms. The first category of algorithms is myopic heuristics such as active scheduling scheme, non-day scheduling scheme, or dispatching rules. Such heuristic algorithms are heavily used in practice. Theoretically constraint programming and meta-heuristics and their hybrid are well studied recently. Finally, I'll show the model for transportation and delivery, called the vehicle routing problem. The vehicle routing occurs at the final part of the SC, the distribution from the DC or warehouse or depots to retailers or customers. A set of customers has to be served by a fleet of vehicles with limited capacities. The vehicles are initially located at a given depot. The objective is to find a set of routes for the customers and returns to the depot without violating the capacity constraint. In many distribution systems, each customer specifies, in addition to the load volume to be delivered to it, a period of time, called a time window that specifies the earliest and latest time to start the service. As in the scheduling problem, many algorithms have been proposed for the vehicle routing problem. The classical approaches are the saving method by Clark and Wright, the sweep method by Gillett and Miller, insertion method, and local search. Recently many metaheuristic algorithms are used for solving difficult real problems. This figure shows the family tree of the vehicle routing algorithms. In 1970 or before, many ad hoc methods have been proposed such as saving, insertion, sweep, and local search. Local search is brushed up to metaheuristics such as taboo search, simulated annealing, and then more general adaptive memory programming that also includes genetic algorithm as a special case. Sweep method that can be seen as a cluster-first route-second approach is refined to generalized assignment heuristics, location-based heuristics that is proved to be asymptotically optimal under some assumptions. Saving and insertion methods that can be seen as construction algorithms have a descendant named grasp that is a construction-type metaheuristics. And we have another branch of exact methods such as set partitioning approach, cutting plane, etc. Recently these algorithms are unified to the hierarchical building block method proposed by me. Conclusion. I have talked about my definition of the supply chain and logistics, 3 decision levels, and then classification of inventory. And then I talked about several models is the SC, they are logistics network design, inventory models such safety stock allocation, inventory policy optimization. Then I showed you the production planning models such as lot sizing and scheduling. And finally sketched the vehicle routing model. I have skipped some important results especially on scheduling and vehicle routing due to the time limit. If you're interested in the skipped parts, please consult the recent books or technical papers or come to my university. That's all. Thanks for your attention.